Okay, so right, so last year we finished looking at reactions of alkanes, which were combustion and which has no synthetic value but it has industrial value, and also free radical halogenation. We mentioned that we looked at the mechanism for the reaction. We also talked about the selectivity of bromine, which reacts in a selective fashion. So bromine prefers the tertiary sites over the secondary over the primary, whereas chlorine reacts in a sort of statistical fashion because it's more reactive, and that prefers to attack the primary sites over the secondary over the tertiary. I did mention then that the reagents, and I guess one of the rules, one of the major ideas, again, is that if I wanted to convert this compound into, for example, let's see what we know so far. So if we want to convert this compound into this one, let's say T, or into this one, D, then I can say several things. I can say if I look at this top reaction, what I'm doing is chemistry at the primary site. I'm converting one of the H's here into a T. So I'm doing chemistry at the primary site. So that's the first thing. The other thing I'll note is that this substrate is an alkane. And there is only one way to make, there's only one reaction that alkanes undergo, which is halogen and light. So my only question then is which halogen? So there is no way out from an alkane except halogen and light. It's the only reaction they undergo other than burning. So if I see a substrate that's an alkane, you should rejoice because I've told you what the first step is. It's going to be halogen and light. In other words, you're thinking step one is halogen and light. The only question is which halogen, what is X? Well, that's going to be determined by where chemistry is happening. Where are you functionalizing? Am I functionalizing a secondary position? Am I functionalizing a tertiary position? Am I functionalizing a primary position? In this case, I'm functionalizing primary, so I want to use chlorine, which has a preference for the primary position. So the first reagent is chlorine and light. Well, all of these things, if you remember, give you a fair range of products, right? I get a bunch of products, including chemistry here, and a bunch of other places. So I want to separate, right, to indicate that I recognize there's several products being formed. You don't have to say how you separate, just that you need to separate. So if I were to do this, I'm going to extend it here. That's going to give me this compound. So chlorine and light and separate will give me the that particular haloalkane where we substitute the primary carbon. Again, remember now, so the product I want to make is the tritio species. So at this point, I can either do a zinc acid reduction, a direct reduction, or I can convert this with lithium in dry ether into the alkyl lithium, and then treat that with T2O, and we're done. If I want to, in fact, let's do another one here as well. Let's say I want to make this compound. If I want to make this one, so I'm going to extend it here. If I want to make this compound, I'm going to ask the same questions, right? What am I doing? So I am taking an alkane. So if I'm doing an alkane, I know step one is halogen and light. I just don't know which halogen yet. And then the second step is going to be separate. So if I give you a substrate that's an alkane, alkanes only give one reaction. There's nothing else you can do with them except halogen and light. So which halogen? Well, that's going to depend on where I'm doing chemistry. At which position is their functionalization? At which position is their functionalization? So we're functionalizing the tertiary product. So in this case, I want my halogen to be bromine, because bromine prefers the tertiary position over all the others. But I will get products where the bromine goes here and here and here. So I will need to separate all those side products from the one that I want, from my target. And that's going to give me this compound. And then I can treat this, again much like that, either with zinc and D3O plus to do direct reduction, or I can convert it into the alkyl lithium. And you notice I am cautious to indicate the conditions of the reaction. That's going to give rise to the corresponding alkyl lithium, which when treated with D2O will give rise to my product. If I want to make this compound, what do I do? Well, I have an alkane, so I know step one is halogen and light. Which halogen? Well, where am I doing chemistry? I'm doing chemistry at the tertiary position. So that means my halogen is bromine and light. I'm going to use bromine and light. Now, there is a reagent, another reagent, which does the equivalent of bromine and light, and it's called NBS. NBS is an acronym for N-bromo-succinimide. Succinimide. And the structure is not important, but it looks like this. And that species essentially liberates Br dot. And if you remember, the bromine is a species, the Br dot, or the X dot, is a species that abstracts H and sort of begins the reaction, right? That's what you get at the initiation stage. So instead of having bromine fractured by light, right, to break the bond this way, what we have is cleavage also, and that gives you Br dot. What we have is homolytic cleavage of that species to give Br dot, and we also make the corresponding radical, right? That is on the end. And this radical is resonance stabilized, right? So it's a resonance stabilized free radical. But if you see NBS as a reagent, it stands for N-bromosuccinimide, which does the same thing as bromine and light. So I'm gonna write this one out and say 1 NBS. Again, I will separate because I'll end up with the bromine here, and here, and here, and here. I don't want this. Now, what that's going to give me is this product, right? Same as that. But what needs to happen now is that my new product, which I want, actually has one extra carbon. So I'm actually going from a lower alkane, remember that? We talked about this a couple lectures ago, now to a higher alkane, an alkane having more carbons. Well, if I'm going to be adding carbons, then this is a Corey-Posner-Whitehouse reaction. So this is tertiary, so I must make it into the nucleophile. So I'll treat it with lithium in dry ether, and that's going to give rise to the alkyl lithium. I'm sorry, that's going to give rise to the alkyl lithium. I will treat the alkyl lithium with cuprous iodide, which will give rise to the lithium dialkyl cuprate. And then I'll treat that with methyl, take your pick, chloride bromide iodide, and that's going to give rise to your target product. Okay? so these are the types of synthetic questions you get. You often start from the alkane and ask you to convert the alkane to some species. Either a labeled alkane, or it could be a higher alkane. And as we get into some more chemistry later on, because we're getting to that point, the range of reactions actually increases. Okay, so we're going to leave this topic, and we're going to start looking at conformations of alkanes, as well as the stabilities of alkanes, of cycloalkanes. Okay, so, and I'll have to walk down there so you can see. So we talk about different types of isomers, and so far the types of isomers that we've met are constitutional. So we had isomers, and so far isomers were constitutional. And a good example would be things like, diethyl, say, methoxymethane or ethyl methyl ether, and that is an isomer of, for example, 1-propanol, which is an isomer of 2-propanol. So all of these are isomers of each other. They differ in terms of connectivity. Who is connected to who? There are sorry. Right. So there were also geometric isomers, and we looked at those. For example, I could have trans-2-butene versus cis-2-butene. Those were geometric isomers. We're going to look at another type now, which is called conformational isomers. And whereas we can say that constitutional isomers differ in their constitution, who is connected to whom, geometric isomers and conformational isomers are similar in the sense that who is connected to whom doesn't change, right? So, for example, here I have a methyl connected to a vinylic carbon, connected to another vinylic carbon, connected to a methyl. So in terms of who is connected to whom, they're the same. They've got the same constitution. But their three-dimensional arrangement of groups is different, right? They've got the same constitution, but their three-dimensional arrangement of groups is different. Okay, in the case of the geometric isomer, that difference is permanent, right? In the case of the geometric isomer, that difference is permanent. Those are permanent arrangements of the two methyls that are permanently stuck on opposite sides of the double bond in the case of the trans, or on the same sides of the double bond in the case of the cis. So I can actually call those, I can say that they have different configurations. Right? So we say that these have different configurations. I could even call them configurational isomers if I wanted. So the configuration refers to the permanent three-dimensional arrangement of groups. Right? Because molecules exist, as everything else does, at least in our universe, in 3 dimensions, spatially. So these have 2 different configurations. These are permanent relative positions of groups across the carbon-carbon double bond. Well, it turns out that there are other ways in which groups can be arranged in 3 dimensions, sharing the same constitution, but those arrangements of the groups are not permanent. So I'll have to walk down, but let me just bring the whole thing here. So I'll have to move between the board and here. I'm assuming you can see me. I'm going to assume you can see me from about here. So what I'm going to do is picture a molecule. For example, could picture a molecule. For example, and I'll draw it out like, take one of these, draw it out like this. So let's say I'm looking at, I don't know, 1,2-dichloroethane. So 1,2-dichloroethane. And we will let the chlorine atom be the red ball. Okay? So chlorine atom is the red ball. And I'm going to build this molecule twice. So here's I'm going to leave the blank bonds to represent H's. Okay? So this is the methylene group, CH2Cl, CH2Cl. So that's my 1,2-dichloroethane. Well, if you remember, we said that in the case of an alkene, right, you can see the double bond. In the case of an alkene, it is not physically possible to rotate about a carbon-carbon double bond. Okay, so if I have an alkene and my groups, whatever they are on opposite sides of a double bond. So let's say I had 1,2-dichloroethene instead, so not ethane, but ethene because of the double bond. Well, these chlorines, or the H's, are permanently trapped across the double bond because we can't rotate about a carbon-carbon double bond because, right, the p orbitals are aligned so that they're in plane, they're coplanar, which means they overlap at the top and they overlap at the bottom, and that forms the pi bond, right? Well, if you would try to break the pi bond, that requires you twisting, right? You'd have to twist this way, which means you lose the overlap. And that overlap is a bond. Atoms like the bond. If you lost the overlap, you have to put the energy in to break the bond. And then the carbons end up not having octets. They'll end up with septets. So if you happen to be stuck on the opposite sides of the double bond, there you stay. That is your permanent 3-dimensional arrangement of groups. Configurations are associated with systems that have restricted rotation. In this particular case, carbon-carbon double bonds. Well, unlike this species, and again I could have had the cis one, right? But unlike the trans species, where the chlorines are on opposite sides, and there is restricted rotation. Here I have now 1,2-dichloroethane. And it kind of resembles the 1,2-dichloroethene, right? The chlorines are on opposite sides, this time of the single bond. But whereas I cannot rotate about the carbon-carbon double bond, I can rotate easily about the carbon-carbon single bond. There is no pi bond that is bracing these two carbons, locking them in place, which prevents rotation. Therefore, I can rotate all day. In fact, these rotations happen blindingly fast at a rate that's roughly 10 to the 9, 10 to the 10 times per second. Right? I mean, that is extremely fast. So rotations are very, very rapid. But here's the problem. If I were to build, for example, we'll have to use our imagination here for a second, and imagine that, let's say red and blue are the same. It doesn't really matter. Whereas I know, so let's imagine that red and blue are the same. So this is your trans 1,2-dichloroethene. This is your cis 1,2-dichloroethene. Well, I'm sorry, one second. Hey, I'm giving a lecture. What's up? Oh, where are you now? Okay, I'm in 306. Okay, all right. Sorry, that's my wife. Let me just open the door. Sorry, right. So here is the cis 1,2-dichloroethene. Here is a trans. They are not interconvertible, right? Because I can't rotate this around because the double bond doesn't allow me. The pi bond doesn't allow me to twist, right, from the trans into the cis. So these are permanent arrangements. How are they different? I mean, physically, how are they different? Well, if these are chlorines, well, I have a dipole moment acting this way that is cancelled by a dipole moment acting that way. So this molecule is nonpolar. It's going to have a low boiling point, a low melting point, low aqueous solubility. Well, this one is polar. I've got a dipole acting this way, a dipole acting that way. So the net dipole, there's a net dipole acting in this direction. So this molecule is polar. It's going to have a higher boiling point, a higher melting point, a higher aqueous solubility than this one. So there are real, tangible differences between these two compounds. They are not interconvertible. These groups are permanently stuck on either the same side or the opposite sides of the double bond. These are permanent arrangements. Well, if I look at the 1,2-dichloroethane, where rotation about the bond is not only possible, it's easy. It's happening 10 to the 11 times per second. So this is easy. Well, in this arrangement, the molecule is nonpolar, right? This dipole is countered by that dipole, much as we saw in this case. On the other hand, this species is polar. Because the two dipoles reinforce each other, I have a net dipole moment. The problem is, although this is a different three-dimensional arrangement of groups from this one, it's not permanent because rotation about the bond is a facile, is an easy process. So these species, this one, right, this one, that one, that one, that one, and all the billions in between where I change the angle slightly, and all the billions in between, those are all different three-dimensional arrangements of groups. But they are interconvertible. They are not permanent, they're temporary. So the term we use to describe that kind of isomerism is conformational isomerism, because we can change conformation by rotation. Okay? So there are several different conformers that are possible by rotating about a carbon-carbon single bond, or any single bond for that matter, where the atoms in the bond have different groups on them. Right? So there's a frame of reference that is set up. So we refer then to this kind of isomerism because these are different entities. This is polar, this is not. These are different entities, different three-dimensional arrangements. The problem is they're temporary three-dimensional arrangements. And more to the point, they're interconvertible. So such species are called conformational isomers of each other. They're called different conformers or conformational isomers. So I'm going to go write that down. They're referred to as different conformational isomers or different conformers. And I might, for example, say there's this conformer, which is different from that conformer. Right? These are conformers of each other, or they're conformational isomers. Right? Same thing. Well, it turns out that we need to find a way to represent those different conformations which exist in three-dimensional space in two-dimensional space. And there's a number of different what are called projection formulas that organic chemists have used to represent those three-dimensional species in two-dimensional space. So there are several different models that organic chemists have used to represent three-dimensional species, as I said, in two-dimensional space. So what do these things look like? There are a couple, and the ones we're going to use more frequently are what are called, again, these are projection formulas. So one of them kind of is the one we had drawn earlier. So let's say I had Cl, Cl, and if you look at it, and I have H's here, H's here, H's here. Okay? So that would represent this one. Well, this one. So I have my chlorine and my other chlorines. I'm gonna come down here again, right? So you can see it. Okay? So hopefully you can see both. So I've got my chlorine up. These are tetrahedral, which means I'm going to have two bonds in the same plane, one in front, one behind. That's a tetrahedral. So I've got the chlorine, the CCl bond, and the CC bond as I'm holding it in the plane, and then coming out of the board, that's a wedge, because as it gets closer to you, it gets bigger, like a fist in your face. And then the dash represents the bond going back into the board. And then on this one, I have the Cl down, so the CCl and the CC are in the plane of the board, plane of the page. And then up and coming out towards you is an H, up and going behind you is an H. So these things are tetrahedral, so you must have that sort of arrangement. I could imagine rotating about the carbon-carbon bond, right? I can rotate about the carbon-carbon bond. And let's say I hold this carbon stationary and I rotate the other one, like so. So I'm going to rotate it 180 degrees to get here. That's going to give me a different conformer, which is going to look like this. So I can use, again, I know these are tetrahedral, so I'm going to bear them in mind. So those are different conformers. And those conformers are in equilibrium with each other. Now, later on in this lecture, probably the one after this, we'll talk about the relative abundance of these conformers. It actually turns out, at equilibrium, there will be more of this one than that one, which we'll get to a little bit later. But there's an equilibrium between these. And that happens at the rate of 10 to 11 times per second. So that's one type of way of drawing these projections. That's one projection form. Some people refer to this, or a version of it, as the sawhorse, particularly when it's drawn like this. So you put the groups down, for example, and you do that, because that, or it's the other way. Here it is. So that would be what you might call a sawhorse projection form. So this is the equivalent of that one. And you do want to practice these. It turns out that there's another one which is very popular, which is called the Newman projection formula. And this requires a little bit of explanation. So what you do is you hold the molecule, so you're looking down the carbon-carbon bonds, right? So looking down the carbon-carbon bonds. I'm going to say, I'm going to represent the carbons on the board, on your page. So holding it like this, let's start with this one. Holding it like this, I'm looking down the carbon-carbon bond. I'm going to represent the front carbon by convention as a dot. I'm going to represent the back carbon by convention as a circle around that dot. So right now that represents a carbon-carbon bond. The front carbon and the back carbon. Okay. What's on the front carbon? Well, looking straight down, I can't see bonds coming out of the board and going back. When I look down this, everything looks flat. Right? When you look down this bond, you cannot see 3 dimensions. You're seeing everything looking flat. So, when I look down the molecule, when I look down the bond, I am seeing a chlorine straight up. I am seeing an H down to my right. I'm seeing an H down to my left. That represents the front carbon. On the back carbon, what do I see? Well, I'm seeing a chlorine straight down, 180 degrees from the one in front. And I'm seeing an H up and to my right, and an H up and to my left. So this species is the same as that species. In other words, what I did here is take my eye and put my eye here. Well, slightly off the angle. I put my eye here. So I'm looking down that bond. So I see, if I'm looking this way, I see the chlorine pointing straight up. This H out and to my left. That H back and to my right. I'm looking this way. That Cl is straight down. That H is up and to my left. That H is back and to my right. That's exactly what I've drawn there. So I can convert the sawhorse type projection formula into the Newman projection formula. Quite easy. Alright, let's use those chlorines as a marker, shall we? And I'm going to ask, if I were, for example, look at